Imagine building an airport on land that didn't exist a year ago. A 20 square kilometer sponge beneath your feet, waiting to settle. China's engineers created the ground the Dalian Jinzhouwan International Airport sits on. Here's how they make it work. By the end of 2025, over 20 square kilometers of new land had been added completely from scratch. But creating land is only the first step. Dalian's old airport was hemmed in by mountains and urban development. For a city that needs room to grow, staying put wasn't an option. Expanding into the sea became the solution. Here's the core challenge. This reclaimed land is a 2.8 billion cubic meter mixture of soil and water. Similar to the world's largest wet sponge, engineers must build an entire airport on top of it. The technical term is consolidation. When heavy structures press down on saturated soil, water slowly squeezes out, and soil particles rearrange over time. This gradual settling is expected, but uneven settling is dangerous. Runways could distort, navigation systems misalign, and foundations shift. To prevent this, engineers carefully sequence construction, use specialized fill methods. What looks like finished land is really a long-term soil experiment, one that could take decades to fully stabilize. And solving it is the first step in building an airport that seems to float above the ocean, yet is firmly grounded in engineering. After understanding why the city could not provide space for expansion, engineers turned to the only place left, the ocean. Here, they had a blank canvas, but also a new challenge. The ground beneath the airport didn't exist yet. Beneath the future runways and terminals lay nothing but soft mud and water, a giant, wobbly sponge stretching for kilometers. This was the canvas China's engineers faced for the Dalian Jinzhouwan International Airport. The seabed is soft, full of water, and constantly shifting. Drop too much weight at once, and it behaves like jelly, sagging unevenly. Engineers solve this with layered reclamation. Sand, rock, and engineered soil are added gradually, letting each layer settle before the next. Think of it as stacking a pile of sponges and pressing them to remove water, slowly turning the whole into firm ground. To speed up stabilization, engineers install vertical drains pipes that allow trapped water to escape faster and carefully monitor the ground with sensors. This ensures the new land consolidates evenly, reducing the risk of runways tilting or foundations shifting. What looks like solid land is really an ongoing experiment in physics and patience. By carefully controlling materials, weight, and drainage, engineers turn the sea itself into a stable, buildable platform. It is a combination of intuition, observation, and decades of soil mechanics, an invisible foundation for one of the world's largest offshore airports. With the reclaimed land in place and settling steadily, engineers face the next challenge, supporting the immense weight of the airport itself. The ground beneath Dalian's offshore airport may appear solid, but it must carry kilometers of concrete runways, terminals, fuel storage, vehicles, and the planes themselves, all without shifting or tilting. Airports are deceptively heavy. A single fully loaded aircraft can weigh hundreds of tons, concentrated on a small patch of runway. Add in terminals, maintenance facilities, and constant traffic, and the total load becomes comparable to a small city. Engineers must understand not just the weight, but how it is distributed across the reclaimed seabed, which behaves unevenly in different areas. The seabed acts like a patchwork sponge. Some sections compress faster, some slower. Uneven compression could tilt runways, misalign gates, or shift foundations. To prevent this, engineers carefully design the layout of heavy structures, plan sequence and timing of construction, and reinforce foundations where necessary, creating a balance between structure and soil behavior. What looks like stable ground is actually the result of meticulous load management. Every runway and terminal sits on soil that has been measured, tested, and adapted for decades of use. Controlling how the airport's weight interacts with the land is as critical as the reclamation itself, and sets up the next challenge, keeping the runways perfectly flat over kilometers. Once the airport's weight is accounted for, another invisible challenge appears: runway flatness. Even minor tilts that cars barely notice become critical when jets touch down at hundreds of kilometers per hour. Runways must be almost perfectly level over kilometers. A slope that seems small to the eye can change braking performance, alter landing angles, or interfere with navigation equipment. On reclaimed land, uneven settlement or tiny shifts in soil could create subtle hills or depressions, turning a smooth runway into a safety hazard. Engineers approach this like building a giant table that must remain perfectly horizontal under variable weight. They divide the runway into thousands of small zones, monitoring and adjusting each section during construction. Materials are compacted to specific densities, and foundations beneath terminals, taxiways, and runways are reinforced with engineered layers to distribute weight evenly. Even small design details matter. Runway edges, lighting, drainage slopes, and taxiway connections must align with extreme precision. Over time, the interaction between aircraft loads and soil behavior continues to be monitored, ensuring the flat surface does not drift out of specification. What looks like a simple strip of concrete is really the result of careful measurement, adjustment, and engineering foresight. Maintaining flatness is the foundation of safe, predictable airport operations, and it sets the stage for the massive logistical systems that will connect the island to the city. Even with flat runways planned, engineers face a more fundamental challenge: how to actually build the island beneath them. You might think they could dump all the soil and rock at once, but the seabed has its own rules. The island is constructed in carefully sequenced layers. Engineers let each section settle and compact under its own weight. This staged approach allows the soil to adjust naturally, turning a soft seabed into a stable platform capable of supporting massive structures. Just like stacking mattresses, add one at a time, press lightly, and let the pile adjust before the next layer. Over years, the layers combine into a solid, reliable surface, one that can safely carry runways, terminals, and all the operational loads of a modern airport. Even after layering, engineers constantly monitor settlement and adjust construction plans to maintain precision. Building the island layer by layer solves the ground problem, but another challenge looms. The ocean never stops moving. Waves, tides, and storms are constantly pushing against the reclaimed land, trying to reshape it. Left unprotected, even perfectly leveled soil would erode over time. Engineers approach this like building a giant barrier against a restless force. Massive seawalls and rock breakwaters line the perimeter, absorbing wave energy before it reaches the airport. The shapes of these barriers are carefully calculated, not only to block water, but to reduce pressure on the soil beneath. Loose rocks, layered in graded slopes, create a buffer that slows erosion, while allowing the ocean to dissipate its energy safely. Even small details matter. The angle of each slope, the size of rocks, and the placement of gaps all influence how waves break and how water interacts with the island. Engineers also account for extreme events, like typhoons or storm surges, designing barriers to handle forces far beyond normal conditions. What appears as a static wall is really a dynamic system, balancing water, weight, and soil. The island is not just built on the ocean, it is engineered to coexist with it, turning a potentially destructive force into a predictable and manageable one. By controlling the ocean at the edges, engineers ensure that every runway, terminal, and taxiway remains safe, solid, and operational despite being surrounded by water on all sides. Protecting the island from the ocean is only half the challenge. Once the ground is stable, the airport still needs to connect to the mainland. Without roads, rail lines, power, and utilities, it would be a fully functional airport, stranded in the middle of the sea. Engineers treat this like building a city in miniature. Every essential service must reach the island reliably, often underground or underwater. Bridges and tunnels carry vehicles and trains, while pipelines deliver fuel and water. Electrical cables and communication lines are buried carefully, protected from waves and corrosion, ensuring the airport can operate 24/7. The design must account for both safety and efficiency. A single failure in a bridge or utility line could disrupt operations, so redundancy is built in. Multiple routes, backup systems, and monitoring sensors are integrated to keep the connections dependable, even under harsh weather. Even the layout of roads and transit within the airport depends on these connections. Taxiways, terminals, parking, and cargo areas are all coordinated so that movement flows smoothly from sea to air to land. What appears as seamless connectivity is actually a carefully choreographed engineering system, balancing geography, logistics, and technology. By linking the island to the city, engineers transform reclaimed ground into a living, functioning airport, fully integrated into the urban and transportation network, ready to handle millions of passengers and tons of cargo every year. Once the island is stable, protected, and fully connected, the question becomes bigger. What does this mean for cities growing along the coast? Space is scarce, and land is expensive. Offshore airports like Dalian's show that it is possible to expand urban infrastructure into the sea without compromising safety, functionality, or precision. From an engineering perspective, the project demonstrates a blueprint for building entirely new platforms on water, carefully reclaimed ground, precise load management, layered construction, and integration with transportation networks. It turns challenges that once seemed impossible into solvable engineering problems. For other cities with limited land, offshore expansion offers a new path. Airports, ports, or industrial zones can grow outward instead of inward, preserving urban space while still meeting demand. Dalian Jinzhouwan is a demonstration of what modern civil engineering can achieve when careful planning meets scale and ambition. It hints at a future where cities reclaim space from the ocean in safe, sustainable, and highly engineered ways.